Okay, good afternoon, everybody. I'm Peter Sommerlad. If you don't know me, Google my name. It's easy to find more information about me. And today I'm here to give a talk on what classes we design and how. And those of you who have been in the same session before, we went very low level to the processor registers and everything. And I try to go a little bit go much higher and giving more on the conceptual side and show only a little bit of code that is not too many details of code, some details, but not too many, but more conceptual thinking on how to actually design classes. For those of you who want to access to the slides, here is a barcode and the URL to get to those. And again, I usually have all my slides on GitHub Talks Pub, on my GitHub on Talks Public, so you can look there if you need more interesting things. And one thing where I might not agree with everybody, but my philosophy is writing less code gives you more software. So, for example, this morning we learned that Matt was actually changing struct to class. I would have stuck with struct because it gives us the most important part, the public part of a class, early on without having to type public colon. And also if you need inheritance, you also don't have to repeat the public before the base classes that you would like to inherit from. So I strive for less, more expressive code, and that's why I'm using struct. Now, what I'm here, let's going higher levels. If you look at the class types that you design, you might find that your types or the instance of the types, the C++ objects, which is the term used in the standard, is actually that the types play different roles or have different properties that make them more or less powerful or more or less useful or give them some additional stuff. And for example, one role that a type can play, it can represent a value. So you have a class type that represents a value, and I will actually what it is in the value, and I will give you a more philosophical point of view of what values are in a moment. And the next thing I want to point out to you is that the C++ object can take the role of a subject. In object-oriented programming, you would call that object, but that term is taken by the C++ standard to denote something that has a value and a location, even if that location is not anywhere in memory. So I use subject, and the subject has a here. So it has a location. So anything that you would call kind of an L value, for example, that has a location. And the type representing that location is actually what I call a relation type. This gives you a location of another subject. The classical example in C and C++ would be a pointer. A pointer refers to some other object, and it's only relevant if that other object is existing. Similarly, a C++ reference would be a relation type that denotes something else, but we also have other relation types. Come to that in a moment. And then there's something specific, and that was one of the things Matt was referring to as the killer feature of C++, the deterministic object lifetime, and having destructors to be called when the object lifetime ends is actually what gives us the power to write manager types, to create manager types that do clean up after they are, or when they are going out of scope or when they are being destroyed. And that cleanup is kind of unique to C++, and this gives us the unique opportunity to have these manager types that automatically clean up at the end, and we will see that's a major part of the talk later on. Now, if you look at value, subject, and relation in particular, if you look at the role of an object that's a value, there is a nice sentence by Michael Jackson, which is not the famous pop singer, but some other Michael Jackson, a Brit, who was writing about structured analysis and design and structured programming in the ages ago. And he says, a value is an intangible individual that exists outside of time and space and is not subject to state change. A value just is. If we think of the value 42, oops. And there's another thing about value types in C++. Scott Meyers told us, when in doubt, do as the ints do. So make your type a value type that behaves like the ints, maybe almost like the ints. The ints have some interesting things, or I would say do it like the ints. So what does it mean that outside time and space, a value can have different representations and it be still the same value? If you look at the value 42, it might be the answer to whatever was asked in the Hitchhiker's Guide to the Galaxy, but we can also spell it out in different ways in C++, in decimal, octal, binary, or hexadecimal, and it's all the identical same value. It behaves the same regardless of how it's represented. And the value is always valid, independent of other entities. That's a big difference between a relation and a value. A relation always needs another object to actually make sense, and the value is just there. We can make a value a subject by forming a relation to it, but otherwise a value is just there. But there's another term related to value in C++ that's important, and that's called value semantics. Value semantics is a property of a type in C++. That is what Scott Meyers said, when in doubt, do as the ints do. And the major feature of that is copyability. And what does copyability mean? It's not just that the copy constructor or some the copy operation is available, implicitly used by the language, but also that the original is unchanged by the copy, and the behavior of the copied value and the original is identical. The observable behavior is identical for a user. And almost all defaults support value semantics directly, and C++ built-in types have value semantics. But be aware, you might have a type that has value semantics that doesn't represent a value. For example, a pointer has value semantics. You can copy a pointer, and both the original and the copy refer to the same object, but they don't have value semantics because they have to they don't have the property of a value because they don't exist outside of time and space. They need the other object they refer to actually be valid and useful. Now, if you look at values and const, there is some meaning where you can, okay, if I make a shared pointer of a const type, it has value semantics, and there are even people approaching value semantics or values with const immutability. One example is Juan Bolivar, who has a nice library for effectively managing immutable values, even large ones, in an effective way. But adding const directly would not always provide you, especially to member variables, doesn't give you type necessarily value semantics. So const is good for variables, but not necessarily for member variables. At least if you want to have nice value types and value semantics. Now let's go for the next thing where the here is important. So what is a subject? A subject is something where identity is important. It has a location, it has a lifetime. So instead of being outside of time and space, it has a space and it has a time where, as long as it lives. In generally, or let's say, many subjects might not need to be copyable because you don't want to copy them. For example, a very big object, you might not want to copy it because it costs efficiency. And very often, subjects are actually target of a relation. So you refer to a subject, you don't want to copy it, but to make use of it, you actually form a relation and, for example, pass a const reference to that object down the call chain. Being a subject or having the ability to form a relation enables us to have polymorphic behavior in the classical C++ way using virtual member functions. And one can say an object becomes a subject once a relation is actually formed to it, once you form a reference, a pointer, or even a smart pointer to it. And then that leads us to polymorphic subject types, the classical way of using virtual in C++, where you have a varying behavior based on virtual member function in a base class, where the derived classes that form the dynamic type of an object actually form the behavior of the object. It is important that you clean up, if you put them on a heap, that the cleanup is done via a virtual destructor in the base class, otherwise you get undefined behavior. And usually you want to prevent copying, because in the base class, if you copy a derived class object via base class reference, what you end up with is a base class object that loses the dynamic type of the derived class. So you want to keep the identity around, so preventing copies, and you want to prevent slicing, which is a mechanism that I just explained. There are other means of dynamic polymorphism which are more modern in C++, and that's not the doesn't fit in the 1 hour talk today. I have given other talks on that, and other people have shown you how to use variant or, for example, type erasure for polymorphic behavior. Now, what are relations? It's not just pointers. And in that model, a mental model I want to establish in you with values, subjects, and relations. A relation represents a subject. It uses the identity of the subject to refer to it, and it allows us what I would like to describe with the German word Fernwirkung. What is Fernwirkung? We look at that in the next slide. And having that relationship to the other object, it allows us, using these relation objects, allows us to use a dynamic polymorphism and abstraction, and it enables us to use non-copyable object. With just value semantics and value objects, you always would pass by value and copy things around. Allowing having relations like references allows us to refer to, let's say, remote things that you can actually use. And that remote part is what I say about the Fernwirkung. If you use a relation object in an expression, it allows that expression to read from or influence an object that is not directly participating in that expression. With values, to make use of values in expression, you always have to use the value directly, like computing 6 times 7, you write out 6, you write out 7, so you have the values spelled out directly in the expression, and then you can multiply them and result as a value again, 42. But with using references or pointers or other relation types, you can refer to something that's far, far away, that is not local to the current expression, and have influence on that. So we already talked about, we have reference parameters, for example, const references that allow us access and copying the underlying remote subject. We have L-value references that are non-const that allows us to modify an object, and we have R-value reference that allows us to steal the guts of an object, and we will learn more about stealing the guts when we look at the manager types. But all that is not only true for references, but also for pointers, for class types that you can form, like span or views or standard string view or iterators. All those types actually, even if they have value semantics, are relation types, and they allow this Fernwirkung on other stuff that is not directly owned by them. Technicalities, so the relation objects actually rely on the existence of a referred entity, and they can become invalid if that referred subject is actually gone. And this usually leads to undefined behavior and dangling, and all these relation types are, I tend to call dangs, because they are dangling, and if they dangle, things go bang, and dang is very similar to bang. To use relation objects safely requires kind of superhero traces in your programmer trait. You have to actually keep track of the related to subject type, subject that you actually refer to, and you have to make sure it outlives the relation as long as you use it. And we have the language relation types, iterators, spans, use, and you name it. And if you have a relation type as a data member in one of your class types. This makes your class type a relation type as well. So it's kind of contagious, like a virus, and but you can alleviate that by actually starting to manage the relationship, and that's when you end up with the manager type. Now, let's look at managers for cleanup. And one guideline, if you start programming your own managing types, always attempt just to manage a single resource. If you want to let's say by hand manage multiple resources, it easily goes wrong, or you miss corner cases where you either lose lose a resource or have dangling or any kind of problematic cases. I tried once with specifying standard unique resource, and I failed. Let's say on my own, I failed to get it right. I got help from others to get it we think is right, but it didn't make it in the standard, but it's available in the technical specification for library fundamentals. And if you want to try, some libraries might implement it, and you can find a scope, let's say unique resource on my GitHub as well. So if you manage a single resource, you have the ability to just manage it as a scope in the scope. So you just locally use the resource and make sure whichever way you leave the scope, the resource is cleaned up, and that's what's called a scope manager. If you want to make it, let's say, be able to transfer the ownership of the resource, that is when you end up with a unique manager. Unique pointer in the standard library is the classical example of a unique manager for transferring ownership of a resource, and the implications we look at in a moment. And then there's the general manager that gives you value semantics for your resource that is managed, and standard vector is something that is there. So having value semantics means that the resource must be duplicable, so you can actually duplicate the resource, and the general manager will allow you to work with the copy as well. Now look at the technicalities. How do you detect the manager? I would say every manager classes are those that have a non-empty destructor, a non-defaulted non-empty destructor. So whenever you program the destructor and put code in the body of the destructor, or the destructor with the body, makes your class a manager class. Today you might have many classes that have a destructor body that aren't managers, and we will see that. And especially if the destructor body doesn't have any statements, it's usually not a good idea to have those. And usually that the resource is defined by a relation type, but that relation type can actually come as a disguise. For example, a manager managing an open file handler or open socket connection actually might represent that as an int, but that int has actually the semantics of a relation type because it refers to a resource that is somewhere else. So it refers to somewhere else in the operating system. So it's kind of a pointer even without being a pointer. So be aware that you might have actually data members that are not pointers or references and still are referring to resources that you manage, like an index in a table or an index in another data structure that you keep around, even if it's not an iterator, just an int. So with the manager type, you have to care about copying and moving. And this is actually where Scott Meyers' rule of 3 came from. When you have a destructor, you need to care about copying. And so my guideline that you should take home, if you take one thing home today, don't have a destructor with an empty body. And there might be some exceptional cases, but you should be very well prepared to argue that your exceptional case where you have a destructor that is not caring about copy or moving, or where you have some special casing and not managing a resource and still do something about it. I usually find those exceptional cases be either bad designs or really made up examples for demonstrating copy and move operations, for example. If you look at Nico Yosuti's book on move semantics, most of the code examples are kind of interesting just to show the individual problems that you might get into move semantics, and not really the best design to use for a problem. If you look at the kinds of manager types, the scope manager is non-copyable and non-movable, and it can be returned from factory functions because we have a copy elision now, mandatory copy elision in C++17 on. But with class template argument deduction, even if it's a generic type, you might not end up to need a factory function. The situation, for example, with the unique pointer where you have the factory function make unique, it's because you have actually the allocation is part of is separate, and you don't want to put that. It's not part of the unique pointers constructor, so you have to have make unique to allocate and create the unique pointer object. Unique managers, they are move only because they transfer ownership, and I'll show you a piece of code how to make that work well. And they are useful when the resources either cannot be duplicated or is very expensive to duplicate, and you want to avoid duplicating it accidentally. And then there's the general manager, where you don't care about duplication, but you might actually provide an optimized version of non-duplicating by allowing the general manager also to have that transfer of ownership optimization with the move semantics. But it requires you that the resource can actually be duplicated to work properly. Now, if we look at why do I talk to you about that? I want you to think about these high-level properties of your class types when you design them, to really make sure that you just don't put everything in a class and then get into messy designs. And think about the class roles and class kinds, and if you refactor your code or work with existing code bases, think if you can put and if you can pinpoint the category for each of your class types. And for example, if you have a class type with value semantics where you don't care about the copy and move operation, they're just the compiler versions work, and then you have defined a destructor with an empty body, that is something you don't want to do. Just delete that empty body destructor. The defaults are just fine and working. And I want to thank you not only for the design of your individual class, but also that if you have a type that has a kind of a special, it's not just value semantics, it allows you to think about the influence of the category of your on your class type. And defining the class types correctly really actually can be overwhelming. People write hundreds of pages on move semantics just to show you what bad things can happen, and maybe tell you also what you can do. And I want to tell you that in a little bit a simpler way with this talk. Just if you look at the special member functions that care about destruction, copying, or moving, you have 5 member functions that are relevant: the destructor, copy, constructor, copy assignment, move constructor, move assignment. And each of those can be either public, protected, or private. So we have 5 times 3 variations of how to, giving us 15. And then each of those functions you can either not declare, you can define it as equal default, you can define it or declare it as equals delete, and you can even define it with a non-empty body by putting something there that does something. And if you multiply that accordingly, I think you end up with 50 different ways to how to, is it, or 43 times 3 times 5 is 45. Yeah, 50 different ways to spell it. And then that doesn't take into account that you actually could have different spelling options, like with or without noexcept, and with or without, what I want to point out, the L-value reference qualification for assignment operators. When you define it, you should make it L-value ref qualified to actually make your type behave as the ints and not differently. Now, if we look at where does this all lead to, if you look at the special rule table, there's an ACCU 2014 talk by Howard Hinnant where this table was presented. I don't want to go into the details right now. There's a 90-minute talk on that by Howard. we have a lot of complicated rules of when you define something, what you actually get, and there are bugs in the standard. And for backward compatibility, which is the killer feature of C++, we cannot actually change the bugs. It just deprecated that if you define a destructor or user declare a destructor, you still get the copy operations, even though, according to Scott Meyers, you should actually care about those. I want to point out the last line because we will refer to that. For example, if you user declare a move assignment operation, even if you declare it as equals delete, you get rid of the copy operations and the move operations at all, and still retain the default constructor and the default destructor, at least the default constructor. That's the most important thing you retain here. Now, if you look at the sub-object influence to our class types, if every member variable has value semantics and is actually a value type, not only value semantics, is a value type, then just putting them together just works. It remains a value type. That's fine. For relation type, they are contagious unless you end up with managing them. For a polymorphic based class, if it's defined well as member, you wouldn't put it as a member, you would put it as a relation. So that's fine if the base is fine. If you have a scope manager as a member variable, then your class becomes a scope manager because copying will not be available. If it's unique manager, your class becomes a unique manager, even without doing anything special, because the copying is prohibited and moving is enabled. And if it's a general manager, it is a value type. So you end up with the first line and everything is just fine. Now, how do we actually define a class? You usually don't declare any of these 5 special member functions that I showed you a couple of slides before. And it is just fine. And this is what it's called the rule of 0. Regardless of your member variables, if you don't do anything special, the rule of 0 should just work fine. Even if you have a data member that's a unique manager, your rule of 0 gives you the ability, okay, my class still behaves like a unique manager, you cannot copy it, but that's fine, it's okay. Everything just works. Unless you must, and when do you do that? I'll tell you in a minute. Now, the core guidelines say, okay, avoid defining special operations too, but the rationale behind that is quite, it's simpler. That's not really a strong motivation. It's a strong motivation, but it's a bit weak to say just so. And this talk is about what you do instead. So what I say is, okay, program in a way that the compiler provided defaults, considering the table that Howard presented, just works. And most of the time it just works. And even if you say, I know what the table says, I just want to spell it out with equals default and equals delete, don't. Because that means you user declare something and it might behave differently, either by changing the overload resolution or the overload set, and also because you might end up with losing properties of your type, like it being an aggregate or being a trivial. And just don't do that. And there are a few exceptions. One thing if you need to resurrect the default constructor because you want to define another constructor, it's okay to resurrect the default constructor with equals default. And provide the initializers with non-static data member initializers, NSDMIs. And the other case is you define a polymorphic base class where you have to declare a destructor and make it virtual. And then you would actually put the equals default as the definition of the virtual destructor in the polymorphic base class. When it's ill-suited, rule of 0, it's actually ill-suited when you have to define your own destructor. And this is actually the base case of the Scott Meyers rule of 3. And in most, you need one case I just said, if you have a polymorphic base class, you need to define a destructor, make it virtual. So you actually deviate from the rule of 0 there. Let's look at that. And the core guidelines tell us, okay, we should use a public and virtual destructor. There are some special cases where you might want to have a protected non-virtual destructor. I usually refrain from doing that because it can be problematic, and you wouldn't put those objects typically on the heap and make them useful. So, for example, type traits, empty classes are cases where you don't apply C35. And preventing slicing is kind of a subject thing. So whenever you have a polymorphic base class, you want to prevent copying, and that means you suppress copying and move. And if we look at that, we have about half a dozen options on how to prevent copying and move, and all of them kind of are either legacy or very verbose. Like, for example, if you look at the at this type in C++, okay, I want to prevent copying, so I define it as deleted, but I also have to not only the copy constructor, but also the copy assignment, because both of them are actually provided for me by the compiler for legacy reasons, even if they are wrong. So I actually have to resurrect the default constructor, because this gets lost when I have to define the copy constructor as deleted. And when I looked at that, the new way of how to do that, it looks much bigger than inheriting from boost non-copyable, but you might not want to have that relation, the thing relying on boost. And I thought deeply with Howard's table and looked at that, and can it be done simpler with less code? Instead of defining 3 operations for just getting rid of 2 of them, can it be done simpler? And the answer is actually yes. Remember, less code, more software. And the answer, I pointed that out, is by actually deleting the move assignment operator. Consulting Howard's table, it's user declared, and that means the other move operation and the copy operations are not there. And we retain the default constructor. So what we usually have, we have a user declared destructor, and to get rid of these 2 wrong things, we delete the move assignment operator, and we are done. And that's the least amount of code, maybe except for inheriting from boost non-copyable, but I think it's fewer characters to type and doesn't introduce the inheritance. So we end up with what I call the rule of DesDeMovA, and it comes from a rule: if a destructor is defined, delete the move assignment. And this is the least amount of code to prevent the copy and move operations of a class. And this comes handy. So a canonical way of defining a polymorphic base class: we have a public virtual destructor that we define as equals default, and a move assignment operator that we define as equals delete, and that you can even put that in the private part of your class. So this is kind of, if we have some virtual member, we have a virtual destructor that is defaulted, and we delete the move assignment operator, and this is the least amount of code to actually conform with the core guidelines preventing copy and move, and have a virtual destructor for a polymorphic base class. And if you define your polymorphic bases today in a different way, think about refactoring thing. Now, how do we implement managers? This is kind of advanced stuff, implementing your own manager types, but actually for scope managers, it's not that advanced. It's just, it looks advanced on the first time. Being a manager, you get promoted, a career step, but implementing managers is actually not too complicated, as long as you're not want to implement a general manager. And we use destructors for resource acquisition is initialization and or scope-based resource management. And those are the classes where the destructor has a body defined. So any class that has an empty body destructor, just delete the destructor. So what does it mean? The constructor will acquire the resource, the destructor releases the resource. Remember, unique pointer is kind of special because its constructor doesn't acquire the resource. But your own managers can actually acquire the resource in the destructor, so they won't need a factory function to make sure it just works. And you need to care about copying and moving, and we will see that in a moment. And my reference to the standard proposal that contains unique resource. That paper also contains scope guards. I think scope guards are a poor man's circumvention of actually implementing scope managers, and I think they are design mistakes. So if you're using scope guard heavily in your code base, considering writing your own scope managers instead that actually do the right thing. Now, if you look at the manager for the resource, okay, we have these rehearse the three categories: scope, unique, and general managers. And now let's look at some real code on how to do that. The scope manager is really a simple thing. I cannot tell you how to acquire your specific resource and how to release your specific resource. That's left as an exercise, but I can show you the rest of your class. You have a private member with the resource, and you have applied the rule of DesDeMovA to get to prevent any kind of copying, and that's how you implement a scope resource manager. Very simple. Almost as simple as implementing a scope guard, and just do it. It's no problem to have many types in your system. Types are free because they only exist at compile time, and having many types is just okay, unless you have too much duplication in your types, but then you make them generic by making them class templates. Now, scope manager, simple, easy peasy going. Now the magic is, oh, move. You don't need to read a 200-something pages book on move. This is just how you do unique managers. So what you will actually do, as a starting point, you need a means to represent an empty unique manager. Because a unique manager transfers ownership, and the original has to have an extra state that denotes, okay, I'm empty, I'm moved from. For example, a unique pointer, if it's moved from, equals the null pointer. It's nothing there, and you can query that actually. And with the unique manager, you need to have a state where the moved from state is actually represented, and you need that because the destructor of a unique manager with a moved from state must not release the resource, only the one that actually holding the resource. And fortunately, we have a type for exactly representing these things. Either something is there or nothing is there, and that's the standard optional type. So regardless of what your resource type is, standard optional is a key to get that resource here, to have that extra state for representing the moved from state of a unique manager. And I factored out some release function, and we will show in the next slides how that actually is used. We have a default constructor. So the default constructed unique manager state is actually the empty, the moved from state, and which is fine, and it just works. And then we have some kind of, that's where you actually have to do your work. It's acquire the resource, and the unique manager constructor with parameters that acquires the resource, and the release function. That's where you resource-specific code actually lives. And I'll show you how to actually implement the move assignment and the move operation and the destructor on the next slide. And this is kind of a rule of three. We have 3 of these 5 special member functions that we actually care about, and where you want to do something special about these functions. And so it's a new rule of 3 for unique managers. Now, how does move actually work? And move is kind of, if you write A, which is kind of an empty box, and move something from B that has a box that is full, what actually happens if you transfer ownership? Afterwards, A has the resource and B is empty. That is when you actually move something by moving the resource. And that is how a unique manager works. And that is the one-line explanation of move semantics. Now, how do we implement that? Well, for the move constructor, we have something, we're creating a new object where we take the ownership of the right-hand side, and we use the move constructor of the optional, which doesn't depending on what kind of resource we have, isn't doing anything that interesting. So it would actually move the resource, which is kind of problematic behavior of standard optional, but that's the way how it's specified. So we actually have to make the right-hand side empty. That's why we actually have to call the reset member function of standard optional to make the right-hand side empty. A better optional would actually have that moving the resource instead of by transferring the ownership to the other and being empty, but that might not be doable depending on what kind of resource. It means the resource has to have some kind of movability of copyability, which is required here already. Now, that is the construction. What about move assignment? First, move assignment, make that L value ref qualified to avoid calling that on temporaries, which might lead up with leaking a resource or losing a resource, or in general, creating an L value reference from something that is a temporary is not a good idea, and this L value ref qualification on assignment operators prevents it. Also, a unique manager should have a move operation that is noexcept to guarantee that you won't actually throw an exception for move operations, which actually you might not know which half or which, if the origin or the target actually owns the resource, or you might actually leak a resource if some exceptional thing happens. And the way we are doing that, we assume that release doesn't throw exceptions. If it would throw, it's called from the destructor as well. So it must protect against catch all exception that might be thrown from releasing the resource. And then we use standard swap, which should be guaranteed to actually not throw exceptions. And it will reuse the swap on the optional, which is guaranteed to not throw an exception if the resource swapping actually doesn't throw exceptions. Now, what we have to do here, because we are releasing actually the resource to prevent actually the self-assignment, otherwise we would actually, from assigning this to this, actually we would leak the resource or we would lose the resource by throwing it away, and therefore we need that self-assignment protection here. And the release function actually checks if the resource is there, if the optional is non-empty, and this is where you put your actual release code here, and you would have to reset the resource like we did in the move constructor with the right-hand side, and so we will clear the optional from the release. And this gives us is all the work that the destructor would be doing, and therefore we just refer to release and call the destructor, call the release member function from the destructor that we define. That's the magic of unique managers. Now, the general managers give me a much harder time, and I won't be able to explain to you what the general manager does for the actual move optimization. If that's you can rely on the strategy that I showed you for the unique manager, but copying the resource depends heavily on if it's on what the resource is, and acquiring the resource as well. But the move optimization, you might end up actually without the move optimization, what you end up if you say A equals B, you end up with the letter being in A and in B. And the optimization is there to prevent the expensive resource allocation if it's expensive. So it would actually leave the right-hand side of the assignment in an empty state. And this is the classic rule of 3 by Scott Meyers. And if you intend to have the move optimization, and with all optimizations, measure before you optimize. So you might not actually need to implement the move operation if the copying is either rarely used or not used in a hot path, or if it's not that expensive anyway. And so move operations for general manager are just an optimization, and you don't have to implement them always. It might not be worthwhile the effort to implement them. And if you implement them, you end up with a rule of 6, or actually a rule of 5 or 6, because it's good style. General manager has value semantics, and usually it means you have a default, it's default constructible to work with everywhere in the standard library well enough, like creating an array of these general manager objects. You have to have a default constructor, and also you have to have an empty state, which should be the default constructed state, because when you want to implement the move optimization. And if we look at more things, so you provide actually value semantics for a resource without value semantics, and it can be expert level codings, especially the cleanup part, and the resource must be copyable and replicable. And think about implementing move twice because it's an optimization, and from Donald Knuth we know premature optimization is the root of all evil. And very often it's much simpler to use general purpose, general manager types like standard vector or standard string just as a member variable, and things just work. As I told you, then you can rely on the rule of zero. Now, if you look at that, sum up the talk, what are the takeaways, which you might have experienced the last 1.5 years, quite often with the lockdowns that we had all, and to keep healthy. We might have ordered unhealthy food, and I hope my guidelines are not unhealthy for your code base, but are actually health food. If you look at the object roles, if you consider those, whenever you create a type that doesn't have value semantics and isn't representing value, so not only the value semantics, but isn't be valid on its own, the objects think twice about that. So whenever you create a type that isn't a value type or isn't a value, think twice, think consciously, so deviate from value semantics and value types only when needed. And the points where you need that is either you create a manager or you want a polymorphic base class, or maybe even a derived class that stays kind of non-copyable unless you do special things or make it a manager type. And you would handle relation objects, especially with care. And that's easy, especially when they are class types and have value semantics like span or string view. It's very easy to return those types and then end up with dangling variables by initializing a variable where that from a temporary that is gone when you actually want to use the variable. So that's where the dang comes in. And usually the relation types are very helpful in as parameter types. First thing, nothing can go wrong unless what you call is a thread function or coroutine in C++20, but otherwise having relation types as parameter types works just fine, but otherwise as a return type, you have to put in thought about lifetime and become a superhero to manage the result that you receive from relation type and manage that wisely. Now, if we look at the special member functions, the biggest thing is rule of zero rules. Don't implement special or declare special member functions, maybe just because your IDE does it for you. Delete such crap. Apply the rule of zero whenever you can. Your classes and even your code efficiency might thank you. Never define a class with a constructor that has an empty body. Get rid of those crap. It used to be a case people are doing that because the IDE generates that maybe even just put virtual there everywhere. And I would say dynamic polymorphism in user level code or where you have to inherit from is kind of a modern C++ code smell. It's rarely used, and even if your code bases do that, consider other things, but that would be a different talk that I didn't manage to put into 1 hour with a lot of stuff. And if you have a virtual destructor, make it equals default. It's very rare that you have an abstraction that also is actually a manager. And otherwise, you end up with a manager when you implement your destructor. And this is where you apply either the rule of DesDeMovA, the rule of three for unique managers with move operations implemented, or the classic rule of three for general managers, or maybe the 6 if you want to have the move optimization and can prove it's actually an optimization. And we've seen in Anders' talk that the compilers are quite good in optimizing stuff and measure before you just put code in there. Remember, less code is more software. What was missing, I didn't tell you a lot about how to cope with the relational objects. That's a separate talk. I have given, and I usually do in my trainings, which are possible to book, and me as a trainer, if you intend to, beware of the dangs and just take home, think about dangs, and when you have them. And I didn't show you how to encapsulate virtual. There's a great YouTube video by Sean Parent where he shows how to work type erasure and create polymorphism without having to implement your own virtual member functions in a generic way. The other option is to actually use a standard variant or a variant type. A standard variant has some issues, and other variants might just work better for you. Or what I said, the type erasure is what I call the envelope letter pattern. That's quite an old pattern applied in C++, dating back to, I think, Barton Eckman C++, which was ancient before the standard, I think even before the standard. Now, I'll leave that slide open so you can actually get a barcode to copy it and get my slides. There's my contact. So if you really intend to get C++ training and then thing. And in the chat, someone said, oh, I might print this table at some point. I hope with my talk, you no longer need to refer to that table because it's really tricky and intrinsic. And you don't want to print out Nico's book and put it on as wall paper on your office. It might not might give you a nice warm feeling to your office by putting it as a tapestry, but it's not actually that you should refer to it every time. And someone said modern IDEs love generating constructors and accessors. Yeah, don't do that. I almost fired one of my assistants when we created develop the IDE for implementing the generate getters and setters code generation, which I think is still in Eclipse CDT and also in develop, and don't do that. I wish you a nice time and will turn off my audio and video soon. And goodbye. Have fun at CPPP, and hopefully we see in person. And I'm very eager to actually attend CPPP in person in the future with that good French food. I'm still waiting for my plateau de fruits de mer or something like that, if that's happening there. Goodbye.